In this chapter, we're going to be studying the idea or the area of chemistry called thermodynamics, which is also covered in physics courses. And that is, for us, the relationship between energy and chemical reactions. And so in our first two sections, we're going to look at different types of energy, that is, categories of energy, and conversions between different types of energy. We're going to look at energy units, which is a simple kind of housekeeping chore. Then we're going to do a quick kind of overview of the principles of thermodynamics, and then we're going to be getting into things that are of particular use for us in chemical systems, and that is the concept of enthalpy, which is a way of measuring energy changes in the laboratory, and also then categorizing reactions as either endothermic or exothermic type reactions. To start, though, we want to talk about why we're doing this, and that is what we're really looking at is why is it that some things occur in the world and some things don't in a chemistry point of view. And so what controls chemical reactions, what controls chemical stability of one type of molecule and not another type of molecule? It turns out there are two broad overall categories of stability and control, and those are thermodynamics and kinetics. Both of those are related and influenced by temperature. So temperature plays a major role in both thermodynamics and kinetic control of reactions. For kinetics, what we're talking about is the rate of a reaction, that is, whether or not it goes fast or not. For thermodynamics, we're talking about the favorability of it, and that is whether it is energetically favored to occur to take some reactants and turn them into products. And so we're really talking about why do some reactants go to make products and those products don't instead react in the opposite direction to make those reactants. So for kinetics, there are two things that matter. Well as temperature as well as activation energy, which is the kind of energy barrier one needs to get over to have a reaction happen, and also the mechanism of how the reaction proceeds, the pathway it goes by, as well as the concentration of the reactants. All of this is covered in Chem 112 in our second semester course. What we're doing here now is talking about part of the thermodynamic portion of the control, and that is thermodynamics is essentially asking, is the reaction favored to occur? Are the products more stable than the reactants? And that depends on two parts, enthalpy and entropy, and those are joined together using temperature. Enthalpy has to do with bond strength and heat transfer between reactants and products. And the thing that matters for stability of molecules is how strong the bonds are. And enthalpy is the portion of thermodynamic control that is governed by bond strength. Entropy is related to randomness or freedom of movement of particles. And those are favored by having smaller molecules more able to move freely than having large molecules less able to move freely. Entropy we will talk about mostly also in the second semester of general chemistry. In this particular right now, we're going to be talking about enthalpy. So in this particular chapter, we'll be talking about enthalpy after we do the kind of survey of basics of thermodynamic principles. Before we do that, let's talk about energy. And energy is categorized into two major types, kinetic and potential. Kinetic energy is the energy of motion, energy associated with motion. Potential energy is associated with position. And so mechanical energy, that is like turning of a crank or a car going down the road, that is bulk matter in motion, and that's a type of kinetic energy. Gravitational energy is potential energy because it's essentially if you have, say, the Earth here, the big E, and you have a rock lifted up here, it wants to fall down to the Earth because there's gravitational pull there, but it hasn't moved yet. So it's essentially latent energy or stored energy by the fact that there's more separation than there might be. Thermal energy is essentially motion energy, but on a molecular scale. So it's based on the random motion of molecules, and that's the type of kinetic energy. And that's the one we're going to be most interested in this particular chapter. Electrical energy is based on the position and movement of charged particles. So it's kinetic energy when those charges are moving, particularly electrons through a wire. And it's also potential based on where you have charges stored in a particular place. Chemical potential energy has to do with the relative positions of positively charged nuclei and negatively charged electrons inside molecules. And it has to do with the fact that sometimes they could be more stably aligned, so there'd be more attractions, or sometimes they're less stably aligned, so there's less attractions. And if there's less attractions, then there's essentially stored potential energy because they could take a form where they would be better attracted. Nuclear energy is a type of potential energy associated with the arrangement of nucleons, protons and neutrons in nuclei. And electromagnetic energy is the energy of light. It's essentially visible light, ultraviolet light, infrared light. Whenever anything happens in the world, it involves transfer of one type of energy to another. So when you drop a rock, if you take a rock and you drop it, say, towards the Earth, what's happening is gravitational energy is being converted into mechanical energy because the rock is in motion. And when the rock hits, it actually is normally going to cause the molecules of the rocks and the stuff it lands on the ground to basically turn into heat. So eventually that turns into thermal energy, mostly. If you use a flashlight, what happens is you have electrical energy that is in your stored battery, which is also can be considered chemical energy. That is turned into actually you start with the battery, which is chemical energy. That's turned to electrical energy with the electrons going through a wire. If you have a regular kind of incandescent bulb flashlight, that's turned into thermal energy. The wire gets hot. That's turned then into radiant energy, which is the electromagnetic energy. Driving a car involves lots of different energy changes. I will leave it to you to figure out what they are. Energy is associated and described with many different units for energy, most of which you've heard of: joules, kilojoules, calories, kilocalories. Kilowatt hours is what's used for electricity bills, and BTUs is often used for heating and cooling appliances in the home. And this is just a chart relating numbers for them, so it's essentially a conversion chart that you use to get from one type of unit to another. If you take, say, a piece of bread has, like, say, 120 calories. The calories you use for food have a capital C, and those are really kilocalories. The capital C food calorie is really a kilocalorie. And let's say we want to know how many joules that is. You would take 120 kilocalories, so it's 120 times 10 to the third calories. And then you would use your conversion between calories and joules. And the way you use this is 1 joule equals 0.2390 calories. So we would say 1 joule over 0.2390 calories, lowercase calories. And that comes out to 120 exponent 3 divided by 0.239. That comes out to 5.0302 times 10 to the 5th joules. 1, 2, 3, 4, 5, yes. So that's how you use it. Okay, now we're going to start talking about the principles of thermodynamics. And the first thing to know is that when you're doing a study in chemistry, the thing you're studying in a thermodynamic point of view is called a system. So a reaction you're doing is called the system. And that's the thing under study. So I'll just say a reaction. So you're doing this reaction. It's the thing that's under study. And everything around it and the rest of the universe is the surroundings. And what we're normally interested in is what happens to the system, because that's the system we're studying. But oftentimes what we actually measure is what happens in the surroundings, because lots of times you can't actually measure what happens in the system, and you let heat or often heat exchange between the system and the surroundings and measure the heat change in the surroundings. So if you were, for example, boiling some water, so you have some water and you're boiling it, it's the water that's the system, and all of the air around it is the surroundings. So whenever you're dealing with a system in a thermodynamic system, you need to define what it is you mean by the system and what it is you mean by the surroundings. There are two different kinds of important categories for the way we define a system. An isolated system means that the system is completely separate from the surroundings and nothing can be exchanged, no matter or no energy. This actually, it turns out, logistically hard to do, experimentally hard to do. So you can do chemical studies with isolated systems, but it's difficult and it's expensive. Much more easy to do is a closed system where energy can be passed from the system to the surroundings, but matter can't. So essentially you have your system, and you have a reaction that happens essentially in a box, and you have the surroundings, and if, say, the reaction gives off heat, that heat can escape, and you can measure that heat escaping into the surroundings because the surroundings will get warmer. But none of the matter that is inside the box can escape. And so most chemical studies we do are on what we would call closed systems. When you talk about energy exchange between systems and surroundings, there are really two different ways that the energy can be exchanged for a closed system. And that is heat exchange, that's Q. Q is always heat exchange into or out of the system, and work done either by or on the system. And work basically has to do with causing things to move. And an example of that would be causing a block to move on a table. But for chemical systems, it would normally mostly be involved with moving cylinders in a like a syringe or in a car cylinder when things are moving. Most of the chemistry studies you do in terms where you're interested in the chemistry itself, you minimize the work, and that's essentially very close to zero. In engineering purposes, where you're trying to, for example, to have a chemical reaction be used most efficiently to turn the turbines or turn the cylinders in a car engine, then the work becomes really important. For most of your study of chemistry in your courses, the work will be negligible and be small, and the E system we're measuring will mostly come out as a heat exchange. The first law of thermodynamics, which is the only law we're going to deal with in this particular course, is simply that there's a constant amount of energy in the universe. That is, the change of energy in the universe when anything happens is zero. So energy lost in one place has to be gained in another place. The idea of that energy can be seen in lots of different places. The result of that energy, it can be the potential energy, or it can be kinetic energy. But whenever anything happens, energy gets converted from one thing to another, but it's not actually lost, and it's not created either. Sign conventions in thermodynamics matter in terms of whether you're talking about things from the point of view of the system or from the point of view of the surroundings, and we're normally interested in the point of view of the system. So if the system is going to absorb heat energy from the surroundings, Q will be positive because the system is absorbing heat. So Q is positive if the system is absorbing heat from the surroundings. If that happens, the surroundings get colder. The surroundings getting colder, it means the system is absorbing that heat. If the reaction actually gives off energy and generates heat, heat is leaving the system. In that case, Q is negative. And in that case, the surroundings get hot. They get warmer. The same is true for work. Work can be done on the system. That is, energy from the surroundings is used to cause something to move inside the system. And in that case, W is positive for the system. Or the system can use its energy to cause something to move. Like the system reaction happens in a car engine, and it causes the piston to move in the car engine. In that case, W is negative. That's work done by the system. Finally, our last aspect to this kind of introduction to principles of thermodynamics is the type of energy that's easiest for us to measure. The type of energy that's easiest for us to measure is enthalpy change, which has to do with the internal energy of the system. That's the energy of the system, how much energy the system has, plus the pressure times the volume, and that's the place where the work comes in. So that's the work term for that. In most cases, this will be negligible, it'll be small. Not always, but in most chemical studies it's small. The reason that this is actually useful is that enthalpy change, the change in this energy of energy measure of chemical entities, is the heat exchanged under constant pressure. And the reason that's important is constant pressure means an open beaker. No high pressure situations. It's hard to do chemical studies under high pressure just from the point of view that you need specialized equipment to withhold that pressure, and also it's dangerous because things under high pressure can explode. And so most chemical studies are done in situations where pressure can be released and stays constant, and enthalpy change is defined as the heat exchanged under constant pressure. So our final part of our introduction here is the difference between endothermic and exothermic processes. In an endothermic process, heat is transferred from the surroundings to the system. So the key here is the surroundings get colder. In endothermic reaction, the heat is exchanged from the surroundings, so the surroundings are losing heat, so the surroundings get colder. So if you do a chemical reaction, and the vessel it's being done in gets cold, that's an endothermic reaction, and the system itself is absorbing that heat as it's reacting. If, on the other hand, the reaction is giving off heat energy, that's an exothermic process, and the surroundings get warmer. Most chemical reactions are exothermic. Not all, but most. Probably around 90% of chemical reactions are exothermic. There's certainly lots of endothermic ones, but for the most part, they're exothermic. Most things that react give off heat when they react. The reason we care about enthalpy and the reason we care about endothermic and exothermic properties is that delta H positive, endothermic, means that the products have weaker chemical bonds than the reactants. That is, in an endothermic process, the bonds are getting weaker as the reaction occurs. If delta H is negative, it's exothermic. The products have stronger bonds than do the reactants. And so this is the reason why exothermic reactions are the majority of reactions, because it's more thermodynamically favored to make things that have strong bonds, and so therefore those processes end up happening more often because things are more stable if they make stronger bonds. So when they do that, they happen. When you make weaker bonds, it's a more rare case where you have reactions that occur to make weaker bonds than in the products, and you start with the reactions. The last thing is that we have diagrams we use to describe enthalpy changes or energy changes in reactions. And the idea is you make enthalpy on the y-axis and the reaction on the x-axis. The x-axis has no numbers because it's like essentially a journey. It's start, end, or it's before and after. So the x-axis is just before and after. It's progress of the chemical reaction. On the enthalpy charts, high up is less stable, low down is more stable. And that's a really important aspect to have just kind of a gut feel for. So when things are going downward, it's more stable. So in this case, the products are more stable than the reactants, and it's exothermic. This difference is the heat lost in the exothermic reaction. In an endothermic reaction, the products are less stable than the products are in terms of bond energies, and this is now the heat absorbed because you're going upward when it happens.